The midterm answers for the written part are already posted on the web, and they are posted as practice midterm 3, just because next time this course is going to be taught, they will have it as a practice midterm. And I'll just go over the midterm and you guys can follow from either document. The first problem was one of your first few homework problems. You are asked to write a single statement that will fill in diagonal elements of a matrix A, a square matrix A with zeros. A lot of you did things like, let me open this. A lot of you did things like diag A equals 0. So diag is a MATLAB function that returns diagonal elements of a matrix. Okay, so it will take a square matrix A, take the diagonals, and return the values in those diagonals as a vector. So this expression returns a value. All right, so you would replace it essentially with the diagonal elements, which will be a vector. So what this, let's say A contains numbers 1 through 4. So what you would be doing is saying 1, 4 equals 0, which is not a valid expression. Okay, you cannot assign a value on the right-hand side, which is 0, into another value on the left-hand side. The left-hand side should be a placeholder, a variable. Okay, it should not be a value. All right. You cannot say 6 equals 5 and hope that you would be storing 5 into this number. Okay? You always need a variable on the left-hand side. So diag A equals 0 does not work. Diag A would help you return the existing diagonal elements of matrix A, but it does not let you store new values in those diagonal elements. Okay? So to be able to enter new elements, new entries, new values into the diagonal elements, you need to use indexing. You need to take the matrix A and provide an index that will refer to the diagonal entries of matrix A and set that to be equal to 0. And we saw this in the first lecture. To access the diagonal elements, you can start from 1, add r plus 1 each time. So the step size will be r plus 1. If you have a 10 by 10 matrix, the first diagonal on the upper left would be 1. The second diagonal element would be number 11, because you go, it'll be number 12, right? 11 or 12? How many say 11? How many say 12? So if I have a 10 by 10 matrix, and the linear index of the first element in upper left diagonal is 10, what would be the next diagonal element? Is going to be 11? 12. Good. So each column will contain 10 entries. The one next to 1 will contain 1 plus r. To go 1 below that, you need to add 1 plus r plus 1. So you start from 1, you add 11 each time, you get 12. And you will move as such until you hit the end of the matrix. So you will say colon end. You start from 1, you go until you get to the end of the matrix. Each time you step with r plus 1, and that helps you access these entries, and you store 0 in them. Okay? There's a few other ways of doing this, and some of you use the I function. So the I function generates a matrix where all the elements are zeros, and the diagonal elements are ones. Let me show you in MATLAB. Okay, I4 is a 4x4 matrix where the diagonal elements are ones and others are zeros. So this is a double matrix, okay? It's a numerical matrix. You can convert this to a logical matrix by wrapping it with the logical data type. You again get the same display, but the underlying data structure is a logical matrix where the zeros are now falses and ones are trues. And then you can use that as a logical index to a matrix that has the same size. Let's assume A is a matrix of 4 by 4, and then you can set that to be equal to 0. So if A is a matrix that has size 4 by 4, you take this logical matrix, you map it, you overlay it on matrix A, and wherever you have true in your logical matrix, you would be accessing the corresponding elements in matrix A. All right? So effectively, you are accessing the diagonal elements again. Make sense? So this is the other solution. There were a few other creative solutions using these ideas, but I'm not going to go over them now. Next problem, there's one little trick to it, but you guys should have gotten it. So a lot of you got this part correct. This is just a concatenation of several different vectors, okay? I'm wrapping all of them in square brackets, which means I'm constructing a larger vector from smaller vectors. So this will be 1, 2, 3, 4. Wrap mat just takes the first argument and replicates it, in this case, 1 times along the rows. So I'm not replicating any along the rows, and twice along the columns. So I will take the vector, I will just repeat it twice. So this will be 1, 2, 1, 2. So this first part was the tricky part. You start from 5 and you try to go to 3 using a step size of 1, and you can never, you don't have any elements in it, right? So we did a few examples of this in the class. You get an empty vector. And as a result, you don't get anything contributing to your larger vector. And the answer remains to be 1, 2, 3, 4, 1, 2, 1, 2. All right? Okay, next problem. A lot of you got it correct because we did examples in the class. But the hexadecimal part, some of you missed. So we have the number 256. You have to think about the largest power of 2 that's in 256, and that is 2 to the power 8, right? So we have 2 to the power 8, and I've already exhausted my number. I don't have anything left. If you take 2 to the power 8 out of 256, you have 0 left, so you've already taken care of your number. And let's see how that maps to binary numbers. In binary numbers, the first one will be 2 to the power 0, the second one will be 2 to the power 1, the ninth one will be 2 to the power 8. So I will have 1, 1, and 8 zeros. 1, 2, 3, 4, 8. Okay? So that's the answer for the first part. For the second part, you are asked to write the same number in hexadecimal notation. So now, instead of thinking in powers of 2s, you need to think in terms of powers of 16s, because hexadecimal means 16. The largest power of 16 in 256 is 16 to the power 2. Okay? So we have 16 to the power 2. And we've already taken care of the entire number. We have nothing left. So you don't need to continue any further. And now we will draw boxes for power 16s. the first box is going to be 16 to the power 0, which is 1. Next one will be 16 to the power 1. Next one will be 16 to the power 2. And we will have a 1 here, because we have one of them only. And the rest will be 0. Okay? So we have 1 times 16 to the power 2, which is 256, plus 0 times 16, plus 0 times 1, and it gives you your decimal number 256. So the answer to this part was 0x. 0x just denotes that this is a hexadecimal number, and then we have 1, 0, 0. All right? Okay, please stop me. I'm not going to go any slower unless you stop me. Okay? All right, next problem is about variable scopes. Let's first change the variable names here, okay? Let me download this. Okay, my computer is acting confused, so just give me a minute. All right, so what I'll do is I'm just going to replace all the variable names to non-confusing names. Okay, but I have to do that consistently. So in the first function apple, I will change all the variable x's with, let's say, p. But I have to do that consistently and make sure that you do that for all the occurrences of variable x. And I will replace all the variable y's with q's. And let's do something similar in orange. Let's replace all the x's with a's and all the variable y's with b's. Okay, so now hopefully your variables won't get as confused with what you have in the command window. So the first function apple takes an input p, and it will return the same input, the same variable. So whatever you do to this variable p will be returned as a result of this function. We have another variable q that has 3 plus p. But after that point, the variable q is never used, right? So it will not change the result of this function. So I might as well delete this. It's not relevant to the problem. And then you multiply the result of the orange with 2 and store it in p, and that's what gets returned from this apple function. Let's see what the orange function does. Orange function takes a variable a, and it will return the variable b, which is 5 plus a. So you take any number, and you add 5 to it, and you return it. So what I will do, I will just, instead of keeping track of different variables and passing them to different functions, I'll just replace this function definition orange p with p plus 5, because that effectively is what's happening when you call that function. All right, so you add 5 to your number and you multiply it with 2, and then you return that same number. So let's do the first part, y equals apple x. you call apple with the value of 5. You add 5 to it. 5 plus 5 is 10. You multiply with 2. You get 20. Apple function returns 20 as a result. And the result is stored in the variable y. So now y becomes 20. So let's replace this apple x function call with y equals 20. All right? So at that point, I have 20 in the variable y. Next, I'm calling the orange function, providing the value of x, which has 5. Orange function takes the input, 5, adds 5 to it, so we get 10. And b equals 10 is returned from this function. And the result is stored in the variable x. So effectively, you are saying x equals 10. And when you print the results out, x will be 10, y will be 20. And that's the answer for this problem. Okay? All right. Now, in the next problem, we will do indexing for a matrix where we have 100 rows and 200 columns. Okay? And we have a linear index 12,345, and you are asked to index the same entry using row-column indexing. So we have a matrix that has 100 rows and 200 columns. The first element will have 1, the last element in the first column will have 100, next one over will start 101, 200, and so on. Okay? At some point you will get to 12,300, and then move on to the next column over and start counting 12,341, and then go down to 12,345. Okay? So this column is going to be 12,345 divided by 100, because that's how many full columns I went through. So you will take the floor of that and then say plus 1. Okay? So you went through 123 full columns, and the next column will be the 124th column. 124 is the answer. Okay? Some of you gave 45 as the answer, and I gave you partial credit, and a lot of you gave 123, and you also get partial credit. Okay? Any questions? All right, the next problem is giving you a for loop, and you are asked to rewrite the same for loop without the same logic, without using for loops. And we did several examples of this in the class. So there are two things that you need to do. First is construct a logical vector that allows you to access this set of entries, the entries that satisfy that logical expression. Okay? And then use that logical vector to index your x, y, z vectors and store the result in M. So I will be a logical vector where I have x smaller than y and x squared, and it's a good idea to enclose these in parentheses, dot squared plus y dot squared equals z dot squared. Okay, the next thing that you have to be careful about is to make sure that these were element-wise operations. So the smaller than sign, you don't need to do anything. It's always, it's going to be element-wise no matter what. The double end, you have to convert it to a single end to make it element-wise, because you want to operate on each element, corresponding elements of these vectors. The square operation, unless you make it element-wise, it would be matrix multiplication, right? So you would, if you don't put the dot in front of the power sign, you would be saying x multiplied by x, which would be matrix multiplication, and you don't want to do that. And the equal sign stays the same. Once you construct this logical vector I, you will have true wherever the corresponding elements of x, y, z satisfy this constraint, and you will have a false otherwise. So you effectively take care of this if-else statements. And the fact that I've removed all the sub-i's, the parenthesis I expressions, gets rid of this for loop, and MATLAB will take care of element-wise operations for me. So I don't need a for loop anymore. So in the next step, I will say mi. I want to index the elements of m where the logical vector I contains a true. And I will say xi dot divide yi. I will take the elements of x that satisfy the constraint, divide them with the elements of y that satisfy the constraint, and you have to do element-wise division. So you have to have this dot in front of it. The next part is you want to operate on the opposite elements, the elements for which I contains a false. Okay, so one way of doing that is to introduce another variable and say j equals not I, or say j equals I equals 0, or skip that step entirely and use not I as your index. So m sub not I equals x sub not I, matrix multiply y not I. Okay? Questions? All right. Next problem. We have a nested for loop, and let's focus on the values of a and b that you get for each iteration, and then we will look at the expression where you make an assignment. So in the first iteration of the outer for loop, a will contain 0. Let me just make a table, a and b. A will contain 0. And then you enter the next, the inner for loop, the value of b will be 10. And then you iterate the inner for loop until you exhaust all the numbers. The value of a stays the same. The value of b is 20. You've gone over all the elements of b. In the next step, you will be taking the next value of a, 510, 520. And for each of these iterations, you are performing a single statement, as shown here. So what does that statement do? On the right-hand side, you construct a matrix. So let's do it for 0 and 10. You construct a 2 by 2 matrix that contains 0, 10, and then a plus 1, which is 1, b plus 1, which is 11. All right, so that's what you get on the right-hand side. On the left-hand side, you store this 2 by 2 matrix in a 2 by 2 matrix of x, and the way you do that is you store it in the next 2 columns of x. So initially, x will contain 2 rows but 0 columns. So no, yes, 2 rows and no columns. So you have 0 elements. In the first iteration, you will be indexing n plus 1, which is the first column, and n plus 2, which is the second column. All right. And then in the first iteration, which rows am I accessing? I'm accessing n colon minus 1 colon 1. The END keyword will be replaced with the number of rows, which is 2. Okay? So 2, starting from 2, going all the way to 1, you have a vector that says 2, 1. All right, so you are accessing the second row of X and then the first row of X. Okay? All right, so which elements of X am I accessing? Let me write that as a matrix too. So these are indices instead of individual elements. So I will be accessing the second row, first column, the second row, second column, first row, first column, first row, second column. All right, so these are the indices of X where these numbers on the right-hand side will go into. So 0 will go into second row, first column, right here. 10 will go into second row, second column, 10. All right, so 1 will go here, 11 will go here. So effectively what you are doing is you are flipping the rows that you are storing into. Make sense? Okay. So you just take whatever is on the right hand side and flip the rows, store it over in X. So we did the first iteration of the inner for loop. In the next iteration, you will just repeat the same thing for the next set of values, which you have 0 and 20. So you will have 0, 20, 1, 21 as your matrix on the right hand side, and you will append that to your matrix X. So you'll have 0, 20, 1, 21. And let me write the whole thing here, the whole answer. So we have 1, 11, 1, 21, 6, 11, 6, 21, 0, 10, 0, 20, 5, 10, 5, 20. And this is the printout that you will get as a result of this problem. Okay? Questions? Okay. All right, next problem is about operator precedence, and some of these examples were straight out of the lecture notes. And the first problem is very similar to last year's midterm. So we have a value x equals 20, and we have the same operation repeated twice, less than or equal to. So they both have the same precedence. You just start from the left-hand side and perform the first one, and then perform the second one. So let's replace the value of x with 20. First, we check whether minus 3 is less than or equal to 20, and the result will be true. And then we compare true with less than or equal to 3. And in a numerical context, the value of true will be 1. So essentially, you are checking whether 1 is less than or equal to 3, and the answer will be true. So you get a 1. Okay? All right. So let me do the second problem right here. So when we have a mixture of arithmetic, logical, and relational, we perform the arithmetic operations first. So those are addition, multiplication, and so on. And then relational operations, which are greater than, equal, or less than signs. And then finally, you do the logical operations, which are and or signs. Okay? So first, we will find the arithmetic operations. We have 1 plus sign here, and there's no other arithmetic operation. So we do that first. 3 plus 1 equals 4. Next, we'll do the relational operations. We have an equal sign and a greater than sign, and then we will just start from left, perform to the right. So 4 equal 4 will give you true. D greater than C will give you true. Okay? And then there's one remaining operation, which is AND. You are ANDing two truths together. The result will be true. Okay? So arithmetic first, relational next, logical last. All right? And if you are coding in your own programs, you're not sure about the precedence, it's safest to put parentheses around your expressions. All right, the next problem is sort of one of the challenging problems here. So we construct a matrix X that has that has 1 row and 10 columns, and it contains numbers 1 or 2 randomly. And some of you have picked on the fact that this is capital X, and this line checks for smaller x, and you wrote down error, and I accepted that also. But that was not really the intention in this problem. Okay, so let's see how rand I works. You have to provide an input, let's say 5. And it'll give you a number between 1 and 5, and it'll give you a random number each time. Okay, so if you say rand I 6, you are generating a random roll of dice. If you provide 2, you will get 1 or 2 as a result. Now, similar to the rand function, this rand I function can generate more than 1 number, and that's done by providing number of rows, let's say 3 rows and 4 columns. Okay. Now you get a matrix that has 3 rows and 4 columns, and each of its elements will be 1 or 2. If you subtract 1 from this, then you get 0 or 1. Okay, so this is a quick and dirty way of getting random logical values. Of course, you can wrap it with logical if you wanted a logical matrix, but even when you don't, this problem will still work as intended. Okay, so we have a matrix of random numbers, and then we perform 2 logical operations on them. One is taking all, which checks whether all of the elements of X are trues. Okay, and if so, it will return true. If at least one of them is not true, then you will get a false as a result. And then we will end that with another function's result, any function, which will take an input, and it will return true if at least one of the elements is true. Otherwise, it will return false. Okay? And if you think about it, not any is actually the same as, well, I won't make that claim. I'll just write down the values explicitly. So what are the options that X could have? Let's make a table again. X could have all zeros. Okay. X could have all ones. Or it could have a mixture of 2. And as far as these 2 functions are concerned, these all and any functions are concerned, there's really no other option. Okay, so you don't really care about the specific combination of zeros and ones. All they will care is whether they are all zeros, whether they are all ones, or whether you have a mixture of them. So what will all give as a result when you have all zeros? It'll give you a 0. When you have all ones, it'll give you a 1. When you have a mixture, you will again get a 0. Okay, so remember, all function gives true only when all of the elements are true. Let's look at the any function. Any function will give a true if at least one of the elements is true. So this will be true, this will be true, that one will be false. In the problem, you are not using any, you are using not any. Okay? So let's write the values that not any will give us. You just reverse the values that you would get from any. So 1, 0, 0. And then you are ending the result of all with the result of not any. 0 and 1. All of X and not any of x equals, if you have all zeros, the result will be 0. If you have all ones, 1 and 0 will again be 0. And if you have a mixture, 0 and 0 will be 0. So whatever values you have in vector x, the result will always be 0. So you don't need to know what this matrix or vector x has. You can safely write value 0 regardless of what that random number generator gives you. Okay? The next problem is testing whether you guys know the definition of XOR. XOR is like and or. It's a logical operation. And it returns true if x and y, if one and only one of them is true. Okay? So if x is 1, y is 0, you get a true. If x is 0, y is 1, you get a true. And in the other cases, you get a false. And this AND is element-wise AND. So it will take two vectors. It will element-wise AND them. And as a result, you will get a vector that has the same size as the two input vectors. 0 and, sorry, let's do the XOR first. XOR of x and y will be 0, 0 XOR 1 will be 1, 1 XOR 0 will be 1, 1 XOR 1 will be 0. And now I will take AND with XOR of not x and y. So let's write not x. Not x is has values 1, 1, 0, 0. And then let's XOR that with y. 1 XOR 0 is 1. 1 XOR 1 is 0. 0 XOR 0 is 0. And 0 XOR 1 is 1. Okay? And then when I AND these two vectors together, 0 and 1 is 0. 1 and 0 is 0. 1 and 0 is 0. And 0 and 1 is 0. Okay? So there is some logical reduction that you can perform to get to the same result, but we won't do that here. You can just iterate over, sort of calculate the result using the logical operations. Okay? Does that make sense? So for this problem, you have to know the definition of XOR, and also know that this element-wise AND returns a vector that has the same size as the two input vectors. All right, let's solve the first programming problem. Edit, get a frame. So this function takes 3 inputs, the number of rows, number of columns, and a symbol or a character. And it will construct a character matrix. So the output should be composed of characters. And the easiest way to do that is to just say out equals repmat s rc. Okay, so you are taking a single character s, and you are replicating it r times along the rows and c times along the columns, and you are effectively generating a box of symbols s. So if s is a star and you have r equals 4, c equals 5, you'll get a 4 by 5 box of stars. Okay, so you have your box. Now let's empty inside of this box. To empty the inside, you need a way to index those elements that are inside. Okay. So how do I index the inside elements? Let me draw this matrix. We have R rows, C columns. I want to skip the boundary and access the inside of the matrix. So I need to skip the first row, skip the first column, skip the last row, skip the last column. So I need to start from the second row, second column, okay, and go all the way to n minus 1th column and minus 1th row. Okay. And we'll take a break after this problem. So out 2 to the n minus 1. Okay, so that iterates over the second row all the way to the 1 before the last row. And second to the 1 before the last column. And store not 0 in them. And I told you guys that during the midterm, you have to put an empty blank space. So that's in single quotes, a blank space. That's the value you want to store in that matrix. Okay? So let's run this, get a frame 4, 5, star. Star gets passed as a value to this function. The contents of the variable s will now be a star. You get your box of stars and then you empty inside this box and you get this frame. Yep. All right. Okay, there is another way of doing this. Well, there are multiple ways of doing this. You can do this using a for loop too, a double for loop, let's say. So for I equals 1 to R, for j equals 1 to R. So let me comment this out. And then you could say, if I am in the first row, or if I am in this, the last row, or if I am in the first column, or if I am in the last column, then out ij equals the symbol. Otherwise, out ij equals the blank space. Okay, and you will get the same result. Oh, I didn't. What went wrong? Oh, here you go. For j equals 1 to c. Let's run it again. Okay. All right, so you could do a nested for loop to iterate over each row and each column, and you can check where you are in the matrix and store a star or a blank space depending on your location. Any questions? All right, let's solve the second programming problem. And I already have this solved, so I need to give a different name to it. So this function will take a DNA sequence as one strand of the DNA and return the reverse complement of it. So what we need to do is replace all the letter A's in S with T. So let's first say out equals S. So out will be a variable, a vector that contains the same elements as S after that point. And then we will find all the elements of S that are A's and use that as a linear index, so as a logical index. So this will be true wherever S contains an A and false otherwise. So I'm effectively accessing elements of out where S contained an A. Okay? And I will store T in those locations. All right? And you will repeat this for all the other exchanges that you will do. Where S were a T, we'll replace it with an A. Where S were a G, you will replace it with a C. And finally, where S were a C, you will replace it with a G. Okay? So this completes the first part. You found the reverse complement, except that we now have to flip it. Let's not forget to do that. Let's just use the flip LR function to flip it, or you could also use linear indexing and say out equals out, start from the end, go to the beginning. Okay, so they will both flip the out vector. Okay, all right, so we found the reverse complement. Now let's find the number of bonds, number of hydrogen bonds that this double-stranded DNA will form. Bonds equal. And we can reuse the same idea. So this S equals A will give us true or a 1 wherever you have an A in your vector. And if you take the sum of those entries, you would be getting the number of A's in your vector. Let me write an example in the command window. Let's say S equals A, C, A, G, A, T, C. Okay, so we have 3 A's in there. If I say S equals A, I will get a logical vector where I have a 1 wherever I had an A in this string S. Okay. And if you take the sum of those, you would be finding the number of A's in your vector. And wherever you have an A, it makes 2 hydrogen bonds. So we will multiply that with 2. So sum S equals A multiplied by 2. That will be the contribution that you get from A complemented by T. And we'll repeat that for the other nucleotides. Wherever you had a T, it will make 2 hydrogen bonds. Wherever you have a G, it will make 3 hydrogen bonds. Plus, let me move to the next row. Wherever you have a C, you make 3 hydrogen bonds. And we will store that in the output variable bonds. All right? Now, to simplify this expression a little bit, you can take the S equals A and OR it with S equals T. And let me write that over here. So S equals A will give you 1s wherever you have an A in your vector. S equal T will give you a 1 wherever you have a T in your vector. If you OR the two together element-wise, then you will have a 1 wherever you have an A or a T. Then you can multiply the number of those with 2, because they will both make 2 hydrogen bonds. And similarly, you can simplify this by saying S equals C multiplied by 3. Okay? All right. Any questions? All right, so the reason I introduced another variable out was the following. Let's say S equals this example string. If you replace all the A's with T's, you would be changing your original matrix, and you will be losing the information that you will need later on. So let's say S equals T equals A equals T. So I'm replacing all the A's with T's. All right? And then when you are trying to replace all the T's with A's in your next step, you don't have your original T's. Your vector has already been modified. So you need two copies of your vector. One, the original one S, and the other one out, where you look at your original values and replace them as correctly. All right. Another idea, if you really insist on using the same vector and not introducing any additional variables, is the following. You can introduce a temporary value, let's say X. So I marked all the A's with X. And then I will replace all the T's with A's, and I will go back and mark and look at the marked items and replace them with T. Okay, but that's sort of more tedious. But if you really insist on not introducing another variable, that's how you can do it. There's a function in MATLAB called strrep that takes a string and what you want to find and what you want to replace it by. Okay, so let's say S equals that, and strrep will essentially find all the occurrences of letter A, replace them with letter T. When you have a single character, when you are replacing a single character with another single character, using logical indexing is preferable. So performing something like this is preferable, or as we did in this solution. If your find and replacement words are different sized or they are longer than one character, then strrep is the better option. Okay? Because then you don't have to worry about how long of a string you are searching and how long of a string you are replacing it with. So let's see an example of that. Let's say S equals apple and orange. And you can find in S all the occurrences of OR and replace them with AND. Okay? So you got apple and orange. All right? But you couldn't do that with something like this. S equals OR equals AND. So this would give you an error because the matrix dimensions disagree. So when you have a single character that you're replacing, use logical operations, logical indexing. When you are searching for more than one character and replacing it with more than one character, then use strrep function. Okay. There are some of the other functions that are described in the lecture notes. Any questions about the midterm problems? Okay, so let's stop that.